And now Pat, our speaker coordinator, is going to give us an introduction for Tyler Cohen.
Okay. Hi everyone, and welcome to our first meeting of the new year. We begin with one of our former club members, Tyler Cohen, whose time spent with us must have had a very significant influence on his chosen profession. Tyler received his undergraduate degree in physics and astronomy from Stony Brook University. At New Mexico Tech, he is pursuing a PhD program. His research interest lies with the North American Nano-hertz Observatory, where they are employing an innovative technique to detect gravitational waves. So please give a very warm welcome to Tyler.
Hello. I was muted. Now you can hear me, right? Can you hear me now?
Yeah, you're good,
Yes.
Tyler.
All right. The universal Zoom greeting. Can you hear me now? Hi, everybody. Good to see you all virtually. It's been a very long time. I'm honored to have been asked to speak here. Yes, I was a club member when I was in middle and high school. And you're right, it definitely did have a huge impact on my chosen career. Yes, I am doing my PhD here at the National Radio Astronomy Observatory in Socorro, New Mexico. I'm in the fifth, I think, gosh, I don't know, fifth year of my PhD. And I work on a project which is very strange. It's kind of unlike anything I've ever worked on before. It's a little bit bizarre. It seems just so crazy that it just might work. So that's what I want to talk to you about tonight. I want to talk to you about my thesis research and the telescopes that we're using to do this research, and just kind of all of the crazy things around trying to detect gravitational waves in weird ways. So I guess without further ado, let's get started. What does gravity look like? To many of you, it might look like the arced flight of a baseball or leaves falling from trees. We see gravity by how it impacts the objects we interact with. But the scope of our perception with the universe is narrow. So too is our perception of gravity. There are black holes on the other side of the universe that we cannot see, yet we know that they're there. How? Gravitational waves are ripples in the fabric of space and time, radiating from the movement of the most massive objects in the universe. To measure them, we need a gravitational wave detector the size of the Milky Way galaxy and made of exotic stars. Tonight, I want to tell you how my colleagues and I are building a gravitational wave telescope out of stars. But to build a gravitational wave telescope, we first need to understand what gravitational waves are. And that starts with Einstein's theory of general relativity. In Einstein's theory, the universe is described by 4 dimensions: 3 dimensions of space and 1 dimension of time. A dimension is just a direction an object can move, like up, down, left and right, forward, back, or forward in time. Now, I'm going to start with the standard science fair bowling ball on a bedsheet demonstration of general relativity. But since the stores were all out of 4D bedsheets, we'll start with a simplified 2D representation of the universe. Okay, so Objects in this 2D universe, they can move anywhere along the surface of this fabric. So they can move forward, back, or they can move left to right, or they can move some combination of the two. But every being that lives on this 2D universe, they're stuck on the surface of this fabric. And fundamentally, objects with mass, like a planet, for example, warp this fabric. Now, here we're only seeing the warping of 2 spatial dimensions. But if we wanted to see what this warping would look like in 4D spacetime, we could do that like this. So this is the 4D analog of what we just saw, right? That bowling ball or our planet on a bed sheet, right? So this is what that looks like in 4 dimensions. Now, of course, as humans, we can't perceive 4 dimensions, so we have to come up with geometric representations. And this representation shows a massive object, maybe our planet, a planet or a star, inside of this cube. But what you'll notice is that the sides of the cube aren't straight, right? And these grid lines are not straight. Closer in toward the massive object, you can see that the lines are more curved than they are further away, right? So this massive object is warping the 3 dimensions of space. But not only is it warping the 3 dimensions of space, it's also warping time. Notice that the clocks that are further away from this massive object are ticking more quickly than the clocks that are closer to it. This is the way that a massive object warps 4 dimensions. But just for simplicity, let's go back to our 2D representation. So if I introduce another object with mass into this universe, like a moon, for example, its path is warped by the presence of this massive object. General relativity shows us that this deflection of objects by the presence of mass is the true definition of gravity, not an attractive force as our experience and introductory physics classes might lead us to believe. To summarize general relativity in 2 sentences, matter tells space-time how to curve, and curvature tells matter how to move. Matter tells space-time how to curve, and the curvature of space-time tells matter how to move. So, the more massive the matter, the more drastic the curvature. So a planet might deform space-time like this, but a star might deform it even more so. And a black hole will pinch space-time to an infinitesimal point so drastically that even light can't escape. Now, before we start making some gravitational waves in our 2D universe, we need to address one more property of space-time. Both our universe and this 2D universe have a speed limit. That speed limit is the maximum speed at which information can travel. Now, the speed of information in our universe is about 980 million feet per second. Nothing can travel faster than that. Most things travel slower than that. And some things travel at that speed. Light, for example, travels at that speed limit, which is why the speed of information is often referred to as the speed of light. And the speed of light and information, it's the same everywhere in the universe. What that means in practice is that 2 parts of the universe cannot instantaneously communicate with each other. And the further away the 2 points in space are, the longer it takes for information to travel from one point to another. So, if, for example, the sun, which is 8 light minutes away from us, were to spontaneously disappear, it would take 8 minutes before the sky became dark. Similarly, it would take 8 minutes before the gravitational effect of the sun's absence reached us and Earth is flung out of its orbit because deformations in space-time, gravitational waves, also travel at the speed of information. Now, I can demonstrate that with the help of my little astronaut friend here by just introducing a massive object into this universe suddenly. And the way that I'm just going to do that is just, just like I did with my fingers before, showing a mass, just going to flick down on the sheet. So there we go. Introduced a massive object into the universe. But that was a little bit too fast. So let's look at that in slow motion. Okay, and stop. You can see that our astronaut is not yet aware of the new massive object that's been introduced, because the warping of space-time is traveling outwards from the source at the speed of information of this sheet. That information hasn't reached her region of space yet. Only now, there we go, does she feel the presence of that massive object. Now, in reality, massive objects don't spontaneously appear or disappear, but they do move. And in particular, they move in orbits. I could demonstrate an orbit just by pressing my 2 fingers down again into the sheet, showing how the massive objects warp space-time, and then just turning my fingers around each other. But I can't go a full orbit, and I can't, do it very quickly. So I have this little model of 2 compact objects, right? We can call them black holes if we want. And I can show how they would orbit each other and how that would warp space-time by just pressing the wheels down into the fabric, pressing the black holes down into the fabric, and turning. This configuration of objects, right, 2 objects orbiting each other, is known as a binary system. Now, you'll notice this binary system is not producing any gravitational waves, at least not noticeable ones. And that's because in order to produce gravitational waves, you either need massive objects or you need a binary system that's spinning very quickly. Now, I can't make these wheels more massive, but I can spin them quickly. But to do that, I'm going to have to bring in some heavy artillery. So I'm going to use this power drill to spin our binary black holes at the speed of information. Fortunately, not the speed of information of our universe, but the speed of information of this 2D universe. And hopefully, we should see them produce some gravitational waves. So there we go, a demonstration of gravitational waves. To produce gravitational waves, you either need very massive objects spinning very quickly, as we've just shown, or or low mass objects spinning quickly, or high mass objects spinning slowly. Now let's take a moment to discuss some properties of gravitational waves and waves in general. But we haven't labeled our coordinate system yet, so let's go ahead and say, just for the sake of explanation, that each of these squares is 1 light year on a side. That is the distance that light and gravitational waves can travel in 1 year. So one fundamental property of waves is the wavelength. Very simply, wavelength is the distance between consecutive peaks of the wave. So if each square is 1 light year, and the peaks of these waves are 3 squares apart, we would say these gravitational waves have a wavelength of 3 light years. Now, another fundamental property of waves, which is directly related to the wavelength, is the frequency. The frequency of a wave is the number of wavelengths that pass by a region of space per unit time. Since we know that the wavelength is 3 light years, and we know that gravitational waves are traveling at the speed of light, we can easily figure out the frequency. So let's count together how long it takes one wavelength to pass by this region of space. We can start at 0 years as the first peak passes this point and count until the next peak passes. So it takes 1 year to travel 1 light year, 2 years to travel 2 light years, and 3 years to travel 3 light years. Let's look at that one more time. Okay, so first peak is passing, 1 year to travel 1 light year, 2 years to travel 2 light years, and 3 years to travel 3 light years. So, since it takes 1 light year to travel, or since one wave passes every 3 years, the frequency is 1 per 3 years. Now, the frequency of gravitational waves is proportional to how fast these compact objects are orbiting each other. If the orbital rate increases, the frequency of gravitational waves they produce increases. Still, we've not quite gotten to the full picture of how gravitational waves distort spacetime. And that's because we're still stuck within this simplified 2D universe. So let's look at what a passing gravitational wave would look like in 3 dimensions. This is what a passing gravitational wave actually looks like distorting spacetime. Of course, it's not blue, and you can't perceive it, and these deformations are highly exaggerated. But if you look at the top of the wave, you'll notice that that's kind of moving in the way that the fabric moved when I spun our supermassive black hole binaries, right? But not only is the wave moving up and down on top, it's also expanding and contracting. And it's expanding and contracting in the opposite direction when it's moving up and down in the other way, right? So while it's getting taller and skinnier, then it's getting shorter and fatter. So one dimension, the up-down dimension, is compressing, while the other dimension, the left-right dimension, is expanding. And we can look at this over top of our 2D demo and just kind of see the 2D and the 4D together, right? And you could see that as the wave propagates, right, these rings are not moving backward and forward, right? But they are moving up and down and left and right. They're expanding up and down and left and right, right? As the peak of the wave passes, they're getting taller and skinnier. And as the trough of the wave passes, they're getting shorter and fatter. Now, what does that actually look like for a passing gravitational wave to distort space-time or an object embedded in space-time? And the way that I'm going to demonstrate that is with a dance. I know it sounds silly, but if you're able to, and if you want to, you can get up and do the dance with me, because we're going to use this dance to explain some more complicated concepts later on, and I actually think it'll help you sort of remember it better. So I'll just give you a second to get up if you want to. You don't have to. Okay, so I want you to imagine for me that a gravitational wave is passing from behind me. It's passing through my body and out of your computer screen. So the wave is moving in the forward back direction. And I'm out here floating in space, and I am oriented in the up, down, and left, right dimensions, right? So the gravitational wave is traveling this way, but my body is kind of floating out in this way. This is what's going to happen when the gravitational wave passes through me. So when the peak of the wave passes, I'm going to get tall and skinny. And then when the trough of the wave passes, I'm going to get short and fat. Peak of the wave coming, tall and skinny. Short and fat, tall and skinny. This is what is happening to space-time and the objects, like myself, embedded in it by a passing gravitational wave. Now, if we combine this dance with our little simple 2D demo, we can get a better understanding of what this actually looks like when the waves pass. So if we want to see what is happening at different discrete points in space, we can combine this dance with the demo. And there we go. Okay. So each tiler is representing what is happening to space and the objects embedded in it at a different point, right, along the path of the gravitational wave. I know the gravitational wave is going out in all these directions, but I want you to just focus on the wave propagating in this direction, right? And as the peak of the wave passes a tiler, he's going to get tall and skinny. And as the trough passes, he's getting short and fat. But while one tiler is getting tall and skinny, right, the trough is passing another tiler where he's getting short and fat. What I want you to notice is that these tilers, they're not getting taller or skinnier. They're not getting fatter or skinnier in this direction, right, the direction that the wave is traveling, nor are they moving forward or backward as the wave passes, nor would any of these tilers measure their clocks to be running at different rates. No. Gravitational waves distort space-time in the directions perpendicular to travel, right? So if the gravitational wave is moving this way, Tyler's getting tall and skinny, short and fat. But nothing is happening this way, they're not moving backward or forward, and the time that they measure is not changing. And we can look at that overlaid with our little blue wormy thing, right? To see what this is happening at a continuous points in space. So the wave is passing through the Tylers, they're getting tall and skinnier and shorter and fatter as the waves are passing. So this is what's happening to space as a gravitational wave passes. Now, while I'm only showing the distortion in one direction, in reality, it propagates out in all directions, away from the binary system, stretching and shrinking everything as it passes. Stars, planets, solar systems, galaxies, and us. The goal of gravitational wave astronomy is to measure this motion, to measure the dance we just did. Remember that the amount of stretching of space-time is related to the mass of the objects, and that the frequency of the gravitational waves is related to the orbital frequency of that binary system. So, by measuring the magnitude and frequency of these distortions, we can understand the binary systems that generated these gravitational waves. So then, how do we measure it? The issue is that all of these binary black holes, they're really far away from us, though perhaps that's for the best, and the strength of the waves falls off quickly as you move away from the binaries. For the binaries we've observed, at distances of millions of light years, the distance between Earth and our nearest star has only changed in distance by the width of a human hair. How could we possibly hope to measure a change in distance that tiny? What if we could send something really fast, that we know always travels at the same speed? If the distance shrunk, it would arrive early. And then if it arrived late, we'd know that the distance expanded. What do we know that always travels at the same speed and is really fast? Light. And that's exactly what the Laser Interferometer Gravitational Wave Observatory does. LIGO has two identical observatories, one in Washington and one in Louisiana. Both consist of two 2.5 mile long tunnels at right angles. Inside these tunnels are 4 mirrors and 2 laser beams. They're kept in a vacuum to keep them isolated from external vibrations and temperature fluctuations. LIGO measures the time of flight of these laser beams so that as a gravitational wave passes, right, and shrinks this direction, this beam arrives early. Shrinks this direction, this beam arrives early. Then this beam arrives early, then this beam. In the characteristic motion of gravitational waves. This is how LIGO detects gravitational waves, by looking for the change in distance of these 2 mirrors using the time of flight of these light beams as a proxy. Now, LIGO is the first experiment to successfully make a direct detection of gravitational waves in 2015, winning it a Nobel Prize. The gravitational waves that LIGO detects come from merging solar mass black holes, the kind that form when 2 massive stars collapse under their own weight. Now, LIGO has made dozens of detections since 2015, ushering in the era of observational gravitational wave astronomy. LIGO opened up a new way to view the cosmos. From the first humans looking to the sky to try to understand the universe until 2015, light, all of the information that we understood about the distant universe, was carried by light. But now we have a new messenger, a new way to study the dark parts of the universe: gravitational waves. But LIGO has its limitations. See, LIGO is really good at measuring gravitational waves from things that are relatively small and spin quickly, right? Like those solar mass black holes. But there are lumbering behemoths out there that escape LIGO's sight. Observational evidence suggests that nearly every large galaxy contains a black hole at its center, 1,000,000 or 1,000,000,000 times the size of solar mass black holes that LIGO can see. These black holes do not form from stellar collapse, like the LIGO black holes, but by merging with other galaxies. And galaxies are merging all the time, all across the universe. Smaller ones merging to form bigger, merging to form still bigger ones. And when these galaxies merge, so do the black holes at their centers, forming supermassive black hole binary systems. Remember, I said there's two ways to produce gravitational waves. You can spin some smaller black holes very fast, or you can spin some giant ones slowly. These are the latter. But here's the key thing that makes gravitational waves from these supermassive black hole binaries different than those detected by LIGO. Because they take so long to merge, there's not just one merging at a time. There's not even a handful merging at a time. No. The combined gravitational waves of all of the supermassive black holes merging over cosmic history of different sizes and frequencies, they add together to form a low-frequency hum of gravitational waves, a gravitational wave background. Allow me to explain with an analogy. Imagine you're eating lunch in a crowded cafeteria, right? It's lunchtime, it's very busy. You can hear the conversations of your friends at your table around you because they're loud and close by. They are the individual sources of gravitational waves, the close by, loud, supermassive black hole binaries. But everyone else in the cafeteria, they form a low frequency hum of gravitational waves. Everyone else is the gravitational wave background, the sum total of all of the low frequency gravitational waves merging over cosmic time. Now, we actually have observational evidence, right? We have estimates for how many of these supermassive black hole binaries are merging in a given time based on looking around with optical telescopes and counting how many galaxies there are. It's like, instead of listening for how many people are in the cafeteria, you're looking around and just counting how many people are in the cafeteria. Based on these estimates for from optical observations, we think that the background hum of gravitational waves is louder than the individual sources. So everyone else in the cafeteria is being so loud that you can't hear your friends. By studying the statistical properties of this loud background hum of gravitational waves, we can begin to understand the history of supermassive black hole binary mergers over cosmic time, and by proxy, the history of galaxy evolution. Maybe we'll find that this hum is louder at low frequencies, indicating that the binaries take a very long time to merge, right? The slower these things merge, the lower the frequency the gravitational waves are. So maybe if we measure much more power at low frequencies, maybe black hole binary mergers take longer to occur. Or maybe there will be an uptick at some frequencies, indicating some loud voices among the crowd. But in order to detect and measure these gravitational waves, we have to be very clever. See, these supermassive black hole binaries, they take years to merge, right? This is what we know from observing optical telescopes observing galaxies merging. They take years to merge, right? And that means that they produce gravitational waves that are light years long. A miles-long gravitational wave detector like LIGO can't possibly hope to detect gravitational waves that are light years long. If only we had lasers being beamed to us from light years away. Well, fortunately, nature has provided these. When a supergiant star, about 20 times the mass of our sun, runs out of nuclear fuel, it can no longer support its weight from the collapse of gravity. And it collapses in on itself. When this happens, electrons are forced into the center of their atoms. And if the core of this star can stave off total collapse, the outer layers will rebound off the core in a supernova explosion. What's left of the core is a ball of neutrons the size of a small city, a neutron star. In this collapse, the star must conserve its angular momentum. Like a figure skater pulling her arms in to spin faster and faster, neutron stars are spun up to incredible speeds, rotating dozens of times per second. The magnetic fields of neutron stars are tremendous. Place a neutron star at the distance of the moon, and its magnetic field would be strong enough to wipe the credit card in your pocket. Now, these magnetic fields accelerate charged particles toward the poles of the star at nearly the speed of light. The acceleration of these particles, it is thought, generates beams of radiation from the star's magnetic poles. If these beams are not aligned with the rotation axis of the star, they swing around like stellar lighthouses. We have a special name for neutron stars whose rotating beams intersect with the Earth. We call them pulsars. Now, pulsars emit only very dimly in the visible light that can be captured by human eyes or optical telescopes. Instead, these beams of radiation are comprised of radiolight, which is invisible to humans. Radiolight is the lowest frequency and therefore lowest energy of light produced in the universe, which is why you need enormous radio telescopes like the VLA to observe them. Now, let me just stop for a moment and clarify. Light waves are waves like gravitational waves, right? Light waves, like gravitational waves, and all waves, remember the demo we did from the beginning, they have a wavelength and they have a frequency, but they're not the same thing. Gravitational waves are deformations in space-time, right? They come from massive objects orbiting each other. And light waves come from things like atoms and molecules wiggling and giving off energy, right? So I'll try to be explicit when I'm talking about frequencies of gravitational waves and when I'm talking about frequencies of light waves. Okay, so if we can't see radio waves with our eyes and we need radio telescopes, what does a pulsar look like to a radio telescope? The bottom panel is what we would see. Every time the pulsar beam points toward Earth, we see a pulse, hence the name pulsar. The shape of this pulse and the spin period, which is the time between each pulse, are our primary sources of information about these objects. This pulse is a cross-section of the pulsar's beam, and so the shape of the pulse gives us information about the shape of the beam. Every pulsar has a different shaped beam, so these pulses are a unique fingerprint of each pulsar. Normal pulsars have periods typically on the order of hundredths of seconds. Searching for these periodic signals in radio surveys of the sky is how we find new pulsars. And by measuring the arrival times of these pulses, by measuring those blips you see on the bottom there, we can monitor changes in the distance between Earth and the pulsar, like the laser arms of LIGO, but on a galactic scale. So, on short timescales, if nothing along the pulsar to Earth line of sight changes, the time between the pulses doesn't change. They arrive regularly, right? So if we look, nothing is changing between the Earth and the pulsar isn't changing distance, nor is anything passing between the Earth and the pulsar, right? So all of these blips, they're spaced out equally. They all arrive after the same amount of time. But if the distance between the pulsar and the Earth decreases, the pulse will arrive earlier. And if the distance increases, the pulse will arrive later. The change in distance and the change in pulse arrival time shown here, it's highly exaggerated. In reality, the changes in pulsar distance due to gravitational waves are about a foot. Yes, you heard me right. We need to know the position of these pulsars to within about a foot if we ever hope to detect gravitational waves. Remember that gravitational waves They are weak, and low-frequency gravitational waves expand and shrink space very slowly. Even though they're spinning very quickly, normal pulsars will eventually slow down on the same timescales as gravitational waves. That means these stellar clocks are drifting over time, so they're not sensitive enough to detect gravitational waves. But there is an exotic class of pulsar which doesn't suffer from this drift. They're called millisecond pulsars. While in general, binary star systems are very common, binary systems with pulsars are not. That's because when one star in the pair goes supernova, the other star is usually obliterated or kicked out of the system. But if the other star survives, you end up with a pulsar with a companion. Now, that's often not great news for the companion, because if the stars are close enough, the pulsar can begin sucking material off the companion star, increasing its angular momentum. It's like pulling a ripcord on the pulsar. Now, if the pulsar can continue to mooch off its companion for millions of years, it can be spun up to thousands of rotations per second, becoming the fastest spinning objects in the universe. With their new lease on life, these recycled pulsars don't suffer from the same drift that regular pulsars do. It would take longer than the universe has existed for one of these millisecond pulsars to slow by even one rotation. So they blink at us with atomic clock level precision, right? The time between the pulses does not change noticeably over even 14 billion years, as long as the universe has existed. So to give you a sense of how fast these guys spin, I'm going to show you animations of a normal pulsar and a millisecond pulsar, along with what it would sound like if the pulses were converted to audio. Those of you with sensitivity to flashing lights, you should turn off your displays and just listen. First is the Vela pulsar. This is a normal pulsar. It's a pretty fast pulsar because it's relatively young. It's in a supernova remnant, but it spins about 11 times per second. So if we were to convert the data that we receive from that pulsar into audio, this is what it would sound like. It's almost spinning so quickly that you can't hear the clicks. But next is pulsar B1937 plus 21, which spins more than 600 times per second. Think about that. These stars, they're the size of a small city. They're the densest objects in the universe next to black holes, and it's spinning 600 times per second, faster than a high-end kitchen blender. All right, those of you with your monitors off can turn them back on now. So now we have a super accurate timekeeper to keep track of the changing distance between the Earth and the pulsar, right? We have these now millisecond pulsars. They're basically atomic level clocks in space, right? They send blinks to us with extreme precision. So we should be able to use them to measure the changing distance between the Earth and the pulsar. We're ready to detect gravitational waves, right? We just need one of these guys and we're all set. Well, if gravitational waves were the only thing changing the distance between the Earth and the pulsar, this would be an easy proposition. But many things besides the gravitational waves can change the distance between the Earth and the pulsar. So, to tease out the specific characteristic motion of gravitational waves, right? To tease out this particular specific, right, the dance, we all know this is how gravitational waves distort space-time now, right? To tease out that motion, we need more pulsars. We need more millisecond pulsars, right? One is not good enough because many things can change the distance between the Earth and that pulsar. So to understand why, we're going to go back to our dance. Now, this time, I want you to imagine that instead of just being floating around in space, I have a ring of pulsars surrounding me, and the Earth is at my center. So I'm surrounded by a ring of pulsars, right? And the Earth is at the center. Like this is our galaxy full of pulsars surrounded by a ring, right? So what is going to happen as a gravitational wave passes in the forward back dimension, right? our Earth and our pulsars in my body, we're oriented in the up, down, and left, right directions, right? So if we do that dance and a passing gravitational wave happens, what's going to happen to the pulsars? Some pulsars are going to get closer to the Earth, while others get further away. And of course, I'm not showing, but the Earth is going like, you know, it's kind of wobbling too in this, but right, the thing we're looking for, right, is the change in distance between the Earth and the pulsars. Right, so as the peak of the wave passes, right, I get tall and skinny, and some pulsars are closer and others are further away. And as the trough of the wave passes, I get short and fat, and the other ones move closer and the other ones move further away. So what that actually looks like when our pulsars are sending back signals to Earth is, right, when the trough of the wave passes, the pulsars above and below the Earth, they're going to get closer to the Earth. And so their pulses are going to arrive earlier than they would otherwise be if it was just a ring of pulsars. Meanwhile, the pulsars on the left and right of the Earth, they've now moved further away. So their pulses are arriving later than we would otherwise expect. Okay, so where gravitational wave is passing, right? And then the peak of the wave passes. And the pulsars on the left and right, now they're closer. So their pulses should arrive earlier. And then the pulsars above and below the Earth, they're further away now, so their pulses should arrive later. This is how gravitational waves are encoded into pulsar signals. This is our gravitational wave telescope made out of pulsars, also known as a pulsar timing array. Now, cartoons, they're nice to help you visualize, but what would it actually look like to detect gravitational waves in our pulse time of arrival data from these different pulsars? This is what it would look like, okay? This is what it would look like to detect a gravitational wave background in our pulse time of arrival data. So on the vertical axis here, what we have is the Toa deviation correlation. Let me break that down for you. That is, for any given pair of pulsars, how similar do their pulse times of arrival look like over time, right? So if two pulsars are close together, right, we should expect their time of arrivals to look similar. We should expect them to be moving in the same way. So we say that they're highly correlated. And then on the horizontal axis, we have the angular separation between any given pair of pulsars. So this graph is showing how do the pulse time of arrivals look for a given pair of pulsars depending on how far they are angularly separated by each other in the sky. Now, you still might be looking at this graph and thinking, I don't see how this shows a gravitational wave background detection in your pulsars. That's the power of dance. So let's remember our pulsar dance. Okay, so for two pulsars separated 0 degrees in the sky, right? So they're right next to each other, right? 0 degrees separation, they're right next to each other. How would they move due to a passing gravitational wave? Well, they would move like this. That's this part of our pulsar dance, right? So they're going up and down together, right? Because they're right next to each other in the sky. They're being affected by gravitational waves in the same way, which means their pulse times of arrivals look similar, or they're changing in a similar way over time. So we would say that the times of arrival of these pulsars are highly correlated, and this graph is at a maximum. Okay, what about pulsars which are separated by 90 degrees in the sky, right? What would that look like? Okay, so that's this part of our pulsar dance, right? One is getting further away, while the other is getting closer. So they're moving not only in an opposite way, but they're also moving in opposite directions. So their times of arrival are completely out of phase. We would say that they are anti-correlated, and this graph reaches a minimum. Okay, so 0 degrees, right? 0 degrees was this, 90 degrees was this. What about 180 degrees? Well, pulsars separated by 180 degrees, they're on opposite sides of the sky. So what does that look like? Well, that's this part of our pulsar dance, right? they're moving closer to and further away from the Earth at the same time, right? Both get further away and both get closer at the same time, but they're moving in opposite directions. So we would say that they're partially correlated. This is a graphical representation of our pulsar dance, right? So this is, right, 0 degrees, 90 degrees, 180 degrees. If you see this trend in your pulse time of arrival data of your pulsars, if you look at all the different pulsars and you make all the different pairs of pulsars and see how their pulse times of arrival are compared to each other, if you see this trend, that is the smoking gun that you have detected the gravitational wave background. This is how the gravitational waves are encoded into the pulsar signals, graphically represented. Okay, so you might reasonably be asking, has it been done yet? Have you detected the gravitational wave background? The answer is maybe. This is data from 13 years of data from NanoGrav's pulsar timing array, right? So for all intents and purposes, the vertical and horizontal axes, they say the same thing, right? This is how correlated the pulsars are, right? This is how much the pulsar signals look like each other based on where they are in the sky and where they are in the sky compared to each other, right? That angular separation, that's on the x-axis. And this blue dashed line here, this is just this curve, right? We know this. This came from our pulsar dance. Okay, so what it would look like if you actually detected this background is that, oh, right, and so all of these, right, all of these points, they're multiple pairs of pulsars binned together, right? And the measured spatial correlations, right? The measured correlations between the pulse times of arrival, those are the measurements here, right? And the lines above and below and to the left, those are the uncertainties in the measurements. Those are the error bars. So if we actually detected the gravitational wave background, we would expect that all of these different pulsar pairs, right? They would follow along the blue curve. They would be doing the pulsar dance, right? We would see that dance in the pulse times of arrival. But that's not really what we see here. You know, there's a lot of noise in this data. We see some, you know, maybe you can kind of convince yourself that it kind of follows this trend, but statistically, we cannot say with confidence that we have detected a gravitational wave background. This is what it would look like if we did. This is a simulation, right? So this is simulated data, a simulated pulsar timing array, but instead of 13 years of data, this is 20 years of data. So what it actually turns out is, unlike, you know, the telescopes that you're used to, a gravitational wave telescope, if you don't do anything to it, if you don't change anything about it, you just keep timing your pulsars, it'll naturally get better over time. If we have a little bit of time at the end, I'll explain why that is. But you know, this is simulated data, so this is not real. We've not actually detected it yet. But this is what it would look like if we did, right? All of the pairs of pulsars, they're all doing the dance. They're all moving in the spatial correlations in the way we would expect them to move in order to detect a gravitational wave background. So why did I say maybe? Well, while we've not detected these spatial correlations, right? This is our actual data, right? While we've not seen these points following the blue curve, what we have seen is low frequency oscillations in the pulsars. Now, those could be due to passing gravitational waves. We do our best to account for all of the systematic errors and other sources of this gravitational wave oscillations that might be causing this. But until we see these spatial correlations, we cannot confidently say that we've detected the gravitational waves. Maybe it'll turn out that this low frequency oscillations, they actually are gravitational waves, but right now we can't say we are sure. Okay, so let's recap. Gravitational waves from across space-time and galaxies slowly merging together, and then the black holes at their centers merge, producing low frequency gravitational waves. All those gravitational waves from all those mergers, they add together in a low frequency gravitational wave background. The way to detect this background is by looking for changes in the distance of pulsars, very specific changes shown by our pulsar dance. if we see those changes encoded in the pulsar signals, we've detected the gravitational wave background. Now, that was a lot. That was a lot to absorb. So I think we've all deserved a 5-minute break. And then, you can get something to drink, use the bathroom. And then when we come back, what we'll do is we'll talk about where and how this is being done and who's doing this work to detect these gravitational waves. So let's all take 5, get a drink, use the bathroom, and in the meantime, enjoy a live feed from out at the VLA site. Thank you for being such a captive audience. That was a lot, and we talked a lot about some sort of heavy physics stuff, now let's take a little bit of a breather and talk about some telescopes. So we've talked about how astronomers are searching for the gravitational wave background, but we haven't talked about who is doing this and where. So there are many different pulsar timing array groups across the globe, but the one I'm a member of is called the Nanograv. We are dozens of astronomers from many institutions and radio telescopes across North America, all working toward the common goal of detecting this gravitational wave background. That's my advisor, Paul Demarest, and me kind of hiding in the back. Until this year, our collaboration used 3 telescopes: the 300-meter Arecibo radio telescope, the 100-meter Green Bank radio telescope, which is shown behind us, and the VLA was used to time a handful of pulsars. Now, in anticipation of some confusion, the pulsar timing array is our gravitational wave telescope, right? We talked about this. That's what the first part of the talk was about, how this dance that we do, the dance that the pulsars do with a passing gravitational wave, encodes their signal into the pulse arrival times of the pulsars. These pulsars have been beaming information about passing gravitational waves to Earth for millions of years. But there needs to be something on the receiving end of those signals. And that has taken until the last couple decades with modern radio telescopes and analysis techniques to be able to interpret these signals and basically plug into this galactic scale gravitational wave detector. Now, to see how these radio observatories work, let's tour some of them, starting 40 miles west of where I'm standing at the Very Large Array. I know I had you fooled at the beginning that I was actually at the VLA, but I'm in Socorro right now. The VLA is located on the plains of San Agustin in central New Mexico. The array is comprised of 28 radio dishes laid out in a Y configuration. This Y configuration follows over 80 miles of railroad track, allowing us to move the dishes to different locations. Now, why would we want to build a radio telescope in the middle of the desert? Now, as optical astronomers, I know you're all familiar with the concept of light pollution. You might think that we don't suffer, right? The skies are very dark, right, out here in New Mexico. But radio astronomers have their own kind of light pollution. It's called radio frequency interference, and it comes from all manner of electronic devices and Bluetooth, the Bluetooth in your phone and the Wi-Fi transceiver in your phone, and even Sirius XM radio, right? All of these things are sources of light pollution that we call radio frequency interference. And this is a problem for radio astronomers, right? So it's a good idea to build your radio telescope out on the deserted plains with the Magdalena Mountains right around you, shielding you from all of this interference coming from electronic devices and things, and cell phone towers. And okay, that's why we built it in the middle of nowhere. But what's with the railroad tracks, right? Why do we need all these railroad tracks? Well, that's because the VLA is configurable. We can move these dishes to different locations. And we do that with some custom-built diesel-powered antenna transporters that we use to reconfigure the array about every 4 months. What for? Wouldn't it be easier to keep them in one place? Well, reconfiguring the array allows us to take very different pictures of the universe by allowing us to change our sensitivity to scale. Here's an example of the same radio galaxy captured with 4 different VLA configurations. In our widest configuration, which is called the A configuration, very creative, shown in the upper left, the furthest dishes are 22 miles apart. That's when we're sensitive to the most fine scale structures, like the superheated plasma being blasted out of this galaxy's nucleus. In our smallest configuration, the D configuration, that's shown in the bottom right-hand corner, we see the diffuse structures like the woofly lobes of the jets coming out of this galaxy. This is a unique ability of the VLA, and it's what makes it such a powerful and versatile instrument. The other thing that makes it such a powerful instrument is the hardware itself. Each of the VLA's dishes are 80 feet across and weigh a whopping 230 tons. Their massive size is what allows them to collect radio waves, like the faint ones coming from our pulsars that we need to time. Let's take a look inside a dish. At the center of each VLA dish are 8 cone-shaped structures of varying sizes. These are the feed horns, and below each of them is a receiver system, allowing the VLA to observe in 8 different frequency ranges of radio light, as low as 1 gigahertz and up to 50 gigahertz. Which of these feed horns the incoming light is reflected into is controlled by an asymmetrical secondary reflector at the apex of each dish. Rotating this secondary reflector will bounce the light off the main large dish into one of the feed horns, thus determining the observing frequency. Now, oh boy, I actually have a feed horn here with me. This one is square, right? This is not one of the ones that was currently on the VLA antenna, but the principle applies. When you're a radio astronomer, or any astronomer, whatever you're looking at, you just want to be looking at that, right? That is what these help us to do. They keep out radio light from unintended directions other than the ones we're pointing. Now, you'll notice that they have, I'll move this a little closer so you can see, there's corrugations on the inside. What these do is these help advance the light wave down the tube of the feed horn, and it allows you to make shorter feed horns, right? And they advance the light wave down to, and I know it's really hard to see, but in the middle there is a little metal needle. That's our radio antenna. Now, all of the, or almost all of the telescopes that I'm going to tell you about have these, and that's what they use to help direct the light into their receiver systems. Below the feed horns are the electronics that convert light into voltages and voltages into digital signals. These are the 8 receivers, one under each feed horn, right? You can actually kind of see the bottoms of the feed horns poking down. The majority of the space down here is actually taken up by dewars and other cryogenic equipment responsible for keeping the important electronics, which are only about the size of a postage stamp, cooled to 3 Kelvin. So most of this space is just pumping liquid helium around in order to keep the receivers cool, right? All those kind of big metal cylinder-looking things. Okay. So next, let's head over to West Virginia to see the Green Bank telescope. The Green Bank telescope is just as isolated as the VLA, but with some additional restrictions. The Green Bank Observatory is situated within the 13,000 square mile National Radio Quiet Zone, where electronic use is heavily restricted. Within 20 miles of the telescope, microwave and cell phone use is outright banned to protect observations from interference. The telescope itself is huge. At almost 500 feet tall, with a reflecting surface almost 350 feet across, enough to fit 2 football fields, the Green Bank telescope is the world's largest steerable single-dish radio telescope. right? Steerable meaning you can actually point the thing by moving it, in altitude and azimuth from horizon to horizon. It can see 80% of the sky with tremendous sensitivity, which is why it's so great for timing these faint pulsars. Now, the optics of the GBT differ from the VLA in a few ways. The primary dish is shaped in such a way that incoming light rays are not blocked by the boom arm or secondary reflector like they are at the VLA. This means that the receivers are not at the center of the dish, but up near the secondary reflector. Oh, and the GBT, notice those feed horns again. The GBT can host up to 8 receivers in a rotating turret in the receiver cabin at the Gregorian focus of the telescope. The GBT covers frequencies of 1 gigahertz to 100 gigahertz, right? So that's about twice as wide as the VLA can observe. But the GBT also has the option to host one of 5 low-frequency receivers at prime focus on a retractable boom that kind of extends out in front of the secondary reflector, shown here. Now, as I said, the GBT can observe up to 100 gigahertz. Now, at these higher observing frequencies, small deformities in the dish become noticeable in the observations. To compensate for these distortions, the surface of the GBT is made up of over 2,000 independent panels. Each of these panels are mounted on actuators at the corners, which can raise and lower the panels to adjust the shape of the dish's surface to a precision of 1/2 millimeter. So at the GBT, they can actually change the shape of this dish to the precision, change the shape of the dish to the precision of 1/2 millimeter. And the last pulsar timing telescope that we'll visit tonight is the Arecibo Observatory in Puerto Rico. Situated in the karst hills 20 miles from the city of Arecibo, Arecibo Observatory used to be the home to the world's largest single-dish telescope, a massive Gregorian reflector with a primary dish almost 1,000 feet across. Arecibo had a very unique design. All of the optics were suspended by steel cables more than 100 feet above the primary reflector. But this meant it wasn't a fully steerable telescope. The telescope's primary reflector is stationary, and the telescope is pointed by moving the receivers and transmitters in altitude and azimuth above the dish. This meant that at any given time, only a fraction of the dish is illuminated, right? As you can see here, right, the light isn't bouncing off of the full dish, only a small fraction of it. And that meant that the observable sky was limited to about a 40-degree strip. But it was incredibly powerful. This is a simple schematic of the optics. The primary reflector was composed of over 38,000 aluminum panels, which are attached to actuators that controlled the shape of the dish. Right, this thing was humongous, 1,000 feet across practically. You can see that light is reflected up from the spherical primary reflector into the Gregorian dome. Now, if we go inside the Gregorian dome, we see the secondary and tertiary reflectors and the feed cabin where the electronics are located. These secondary and tertiary reflectors were specifically shaped to correct for the spherical aberration created by the fact that in this configuration where you've got your receivers hanging above your primary reflector, right, and it's a spherical reflector, there's no way to put your receiver systems at the prime focus unless you have specially shaped secondary and tertiary reflectors, which is what is shown here. Above the tertiary reflector and below the feed cabin, we can see the bottom of the receiver feeds sticking out. Everything at Arecibo in the feed cabin is upside down compared to the VLA and Green Bank, right? So this is pointing down toward the dish. Since the light is bouncing up from the tertiary reflector underneath the receivers, all of the feeds, all the feed horns, all the dipoles, they're facing down. Now, if we take a walk inside the feed cabin, we can see the top of the receiver systems and their electronics. Again, most of the volume here is taken up by cryogenics, which pump around liquid helium used to cool the electronics and the receivers to 15 Kelvin. The rotating turret in here hosted 9 receiver systems, including a 7-beam camera called Alpha, which was made by CSIRO in Australia. That's the one we're looking at now. That's why it had a little plushy kangaroo on top of it. Wonder what happened to that kangaroo. Okay, that's the inside of the feed cabin where all the receivers are. This is the 96-foot, 430 megahertz line feed that was used for ionospheric radar and sometimes pulsar observations. It had the advantage of illuminating the entire dish, but with an intrinsically narrow frequency range. The line feed snapped off and blew away during Hurricane Maria in 2017, and nobody actually knows where it landed, but I suspect some farmer in Barrio Esperanza now has a very expensive lawn ornament. My time in Arecibo was vitally important to my development as a scientist and as a person. The observatory scientists and staff were the first people to treat me like scientists rather than a student. Well, actually, Westchester astronomers did that as well. It gave me the confidence that I needed to stay in the field. I had a couple rough academic semesters before I started my internship there, and I was kind of wondering whether or not I would stay in astronomy. And then I got this amazing opportunity to go to Arecibo. While at the observatory, I would hang around the control room, waiting for any opportunity to go up to the platform. Receiver needs capping? Yeah, I can help with that. The feeling of being positively puny in comparison to the platform and dish below was exhilarating. And the views of the evening mist over the karst hills were breathtaking. It still remains my favorite place in the world. When my internship there ended, all I could think about was how to get back to Arecibo. So I went to graduate school for radio astronomy in the hopes of someday being able to work at the observatory again. Okay, so we've gotten a little bit of a look at some of the telescopes that Nanograv has used to time these pulsars. Where are the pulsars? These here are the 80 pulsars that we use these telescopes to time, the ones that make up our pulsar timing array, in relation to the rest of the galaxy. You'll notice they're all pretty close to the solar system. The closer a pulsar is, the brighter it appears, and the less stuff there is blocking your line of sight to it. Now, we observe these pulsars very often. We have to, in order to tease out that faint gravitational wave signal. This is a map of the sky, with the pulsars being denoted by triangles. Each blink is a week's worth of observations between 2015 and 2017. Red triangles were observed at Greenbank, blue ones observed at Arecibo. I know this is all blinking by really fast, but I just want you to get a sense of just how vital frequent, consistent observations are to maintaining gravitational wave sensitivity. Altogether, we observed half of the pulsars with Greenbank and half with Arecibo. At least that was true until this year. I sort of buried the lead a little bit, but maybe some of you noticed I spoke about Arecibo in past tense, or maybe you were already aware that this telescope doesn't exist anymore. On the morning of August 10th, 2020, one of the auxiliary steel cables supporting the platform detached from its socket, tearing a 30-meter gash in the dish below. Observatory observations were suspended pending an investigation and repair. It was the last time the observatory would be open. Then, on November 6th, things got much worse when one of the 4 3-inch thick main cables on the same tower outright snapped. The contracted engineering firms determined that there was no guarantee the remaining cables would hold the platform's weight, and the National Science Foundation decided that for safety reasons, it would dismantle the observatory in a controlled demolition. In subsequent weeks, radio astronomers across 4 generations met online to brainstorm ways to save the Arecibo Observatory. But neither we nor the NSF would ultimately determine the telescope's fate. On the morning of December 1st, the remaining cables from the tower snapped, and the platform swung into an adjacent rock cliff, tearing off the tops of the suspension towers and reducing the telescope to rubble. There's videos of the collapse online if you want to watch them, but I won't show them to you because honestly, I haven't and still can't bring myself to watch. People I know who work at the observatory tearfully described it as sounding like the end of the world. Fortunately, nobody was injured. My morning for Arecibo and my future employment there was cut abruptly short by a very pressing concern, which is that half of the observing time for nanograph's pulsars, right? We timed half of our pulsars with Arecibo. Half of our observing time was gone. How are we going to time these pulsars? Where are we going to time these pulsars, right? What telescope can compete with Arecibo's sensitivity? So that's kind of where my role comes in to Nanograph. I'm sort of a strategist, if you want to think about it that way. Part of my thesis is to figure out what the optimal balance between observing resources is, right? Pulsar timing is all about balancing observing resources. It's about finding new pulsars and timing them, of course, but it's you know, telescope time is expensive and there's limited telescopes in the world, right? So how do we balance those resources? Green Bank, right? It can see nearly the whole sky. Arecibo has a much more restricted view of the sky, but it's more sensitive. So after the Arecibo collapse, right, we have this pressing concern. My advisor and I are tasked with coming up with a new observing strategy, and quickly, because with every month that passes without getting observations from these 40 pulsars that were timed at Arecibo, we're losing sensitivity to gravitational waves. So we had to come up with an observing plan. Now, we couldn't test each of these pulsars by observing them at the different telescopes for different amounts of time and seeing which ones work best, because there's 80 of them and there's limited telescope time, and that would be very slow and inefficient and expensive. So my specialty is coming up with optimal observing strategies via computer simulations. So that's what I did. I created simulated a galaxy of pulsars, and I put models of all of Nanograph's pulsars that we observed in it. And then what I did is I simulated observing campaigns with hundreds of different configurations of observing campaigns with different telescopes to see which was the optimal observing configuration in order to maintain or at least mitigate the loss of sensitivity to gravitational waves. So I did that, and I ran those different timing observations inside of the computer, right? Much more efficient than actually trying to observe them with all the different telescopes. And this was the optimized strategy that we came up with, right? So we started out timing 37 pulsars with Green Bank, right? This was before the Arecibo collapse, and 39 pulsars with Arecibo. 37 with Green Bank, 39 with Arecibo, and then two with both, just for test purposes. So the strategy we came up with, because now Arecibo doesn't exist anymore, Arecibo exists, but the telescope doesn't. We removed 7 Arecibo pulsars from the array because their contribution wasn't worth their telescope time. 41 pulsars would split observations between the Green Bank telescope and CHIME. That's the one shown in the upper right. That's a new telescope in British Columbia, which could time up to 10 pulsars at once. So a lot of our pulsars went there. 15 pulsars would split time between the VLA and Green Bank. 18 would be timed only with Green Bank, and then we would time our best pulsar everywhere. We began this new observing strategy this past spring, in the spring of 2021. Now, we will take a hit for the 6 months without any observations of those 40 pulsars and the ultimate loss of Arecibo, but we mitigated disaster for our experiment, right? We're back up and running, we're back to observing all of our pulsars. Preliminary analysis of our next data release, containing 3 more years of pulsar time measurements, is ongoing. And we've not yet ruled out that the gravitational wave background is in our data, right? Those low frequency observations, we can't say whether or not that is what we've actually detected until we see those pulsars doing the pulsar dance, but we haven't ruled it out yet. Ultimately, we're confident that with the next generation of radio telescopes, pulsar timing will churn out gravitational wave detections on the regular. But we'll just have to wait and see. Okay, thank you very much. Thank you for your attention. Been a very good audience. And now I'll take some questions. I'm sure there's probably a lot of them.
Yeah, thanks for such a great talk and such great graphics. So if you have a question, you can either just jump in, or if you can't get to that, just type something in the chat and I'll call it.
Well, let me start by just sharing the tragedy of Arecibo, but I know that there has been, when it happened or shortly after it happened, some discussion about trying to think about rebuilding it at some point. So do you know anything about that?
Yes, so I have been a part of that discussion. So I kind of sort of worked on two things. I didn't really talk about this very much, but I guess I can a little bit. In the wake of the Arecibo collapse, I was kind of working on two things, right? I was working on mitigating the impact of the loss of the telescope for our pulsar timing array, but I was also working on building an Arecibo replacement, the next generation Arecibo telescope. And what we ended up doing is the National Science Foundation asked us to submit a white paper, which is basically something that astronomers write to give scientific justification for why they want to do an experiment or build an instrument. So that's what we did, and we submitted that to the NSF. The difficult thing is the collapse of the Arecibo telescope could not have come at a worse time, because the way that funding works in astronomy is every 10 years, there's a survey of the astronomy community, that the funding that, the community puts forth their priorities, and that is what informs the funding agencies to set their priorities to fund the telescopes. And that's done every 10 years, right? JWST was part of the 20-aughts decadal survey. Unfortunately, the collapse of Arecibo happened after the 2020 or 2021 decadal survey was completed. So the funding agencies had already set their priorities for the next generation of telescopes. The community had agreed at this point, after the collapse of the telescope, that these were the telescopes, the ones that had been outlined in the proposal, that would make up for the loss of Arecibo. So right now there is no funding for it. We have a design concept. There was a workshop over the summer where people sort of met to work together on a new design. Of course, the funding is needed for engineering feasibility studies and other things like that. So there is a design, but there's no funding for it right now. We're looking for alternative sources of funding, maybe. I'll just say one more thing really quickly. I know this has been a long answer to your question, but Arecibo is not just important for the astronomy community. It's vitally important to Puerto Rico. It provides educational opportunities for people on the island. It's sort of like a cultural source of pride. So it's really vitally important to the island, and also the astronomy community.
So we have a couple of questions in the chat. John Markowitz is asking, is the large new radio telescope in China doing similar observations of millisecond pulsars?
So yes, they actually are. So for those that don't know, a few years ago, China completed their FAST telescope. I'm blanking out what the acronym stands for. FAST, or 500 meter. I don't know. It's 500 meters across. So it's bigger than Arecibo, which is great. And they are doing pulsar timing observations there. Nanograv is part of. So there's all these individual pulsar timing arrays around the world. Nanograv is one of them. There's also one in China, and kind of all of them work together. And I didn't really get to talk about this. They all combine their data into what is called the International Pulsar Timing Array. And this Chinese telescope is a part of that. As far as doing it being a sufficient replacement for Arecibo, as far as I know right now, although this might be changing in the near future, they don't have open skies time, which means like, competitive time that's not allocated for specific projects that people can compete for, which is what Arecibo had, which is why we did so much of our observations there. So that may, in the long term, prove to be a viable replacement, but right now, even though they are doing pulsar timing, at the immediate moment, it's not a replacement for Arecibo.
And what
It's a
about
great question.
the radio telescopes in Australia?
The square kilometer array is also doing pulsar timing, and that's part of the Parkes pulsar timing array, the PPTA. Again, there's all these different groups, right? Nanograph, we're just one of them. There's all these different groups around the world. The Parkes pulsar timing array is the one in Australia. So they use the Parkes telescope. They use the square kilometer array, which is in South Africa and in Australia. Yeah.
But
These groups are all over the world.
They probably don't see the same pulsars that you do, though, because they're looking
right.
Hemisphere.
And that's what's great about the IPTA is the fact that they have access to the southern hemisphere pulsars, and we have access to the northern hemisphere pulsars. So if we combine all of our data, we've got a much bigger pulsar timing array than we would otherwise have.
So we have another question from Louise Gantras. Is there a possibility to use gravity waves as propulsion? Sort of harness the energy somehow.
That's a really good question. I would say not in anywhere near the immediate future. So in order to generate gravitational waves, right? So first of all, gravitational waves very, very weakly interacting with matter, right? There were experiments and are still experiments ongoing to try to detect gravitational waves in physical materials, right? But they're very weakly interacting with matter, particularly when you're far away from the source. But in order to get an appreciable amplitude of gravitational waves, you either need really, really massive objects, right? You need supermassive black holes, or you need to be able to spin your solar mass black holes near the speed of light. So you're not talking about, civilizations or intelligences that are, planet scale or solar system scale or even like local, you're talking about galactic scale civilizations, which have, the energy, right, to be able to spin, would need the energy to be able to spin supermassive black holes or spin solar mass black holes near the speed of light, which is really, really, really hard to do and would require a tremendous amount of energy. So as a viable option for like, near-term propulsion, I would say probably not, for those reasons. But who knows? Maybe there's, you're talking about, Kardashev scale civilizations out there. Maybe there's a galactic scale civilization who's making use of gravitational waves, but not in our near future.
And we have a pretty high-tech question here from Joe Lyle. Can you comment on how the pulsar timing array will contribute to understanding the final Parsec problem?
That's a great question. Yeah, I kind of alluded to it a little bit, but I didn't really touch on the final Parsec problem. The final Parsec problem has actually sort of been solved. We're pretty sure we know the solution to it. So just for the people that don't know, here's what the final Parsec problem is. Why don't I go back to pull up a graphic or something to have something visual to go along with it. How about this one, right? So you've got these supermassive black holes merging at the centers of galaxies, right? The gravitation from these galaxies, that causes them to merge together, right? And when they do, their black holes merge. Now, when these black holes merge, there's a certain amount of gravitational energy in the system, right? And the way that the black holes get closer and closer to merging, not only is there, stuff orbiting around these black holes in the individual galaxies, but there's, like physical things like stars and planets and stuff like that, but there's also gas and dust. And the final Parsec problem is, or let me take a step back and say that when these black holes merge, they kick stuff out of the system, right? These stars and this gas, if it doesn't get consumed by the black holes, it gets kicked out of the system, changing the gravitational potential energy of the system, and that moves the black holes closer together. But there's a question, which is, what allows these black holes to overcome the final parsec? Is a distance of measurement in astronomy that's equal to 3-point-something light years, right? So how do these black holes merge to overcome that last little bit of distance? And people looked at, basically the way people answered this was, or think that they've answered it, is by looking at, which is amazing that we can do this, is to actually look at like dynamical movements of stars around these black holes as they're merging, and see as the black holes merge, what is happening to the stars. And I think, I don't know if the question has been completely resolved, but the understanding is that, the dynamical movements of these stars and getting kicked out is enough to overcome that final parsec to allow these black holes to merge. But I think pulsar timing arrays, in understanding the timescales of these gravitational wave mergers, and understanding how these supermassive black holes merge, will help to solidify that understanding of what actually allows these black holes to overcome those last few light years and merge together. It's a great question.
Okay. So maybe can everybody join me in thanking Tyler for a fantastic presentation.